In this presentation, there will be 4 sections. First, introduction, which is reserved for the BEMD decomposition in general, with obstacles encountered during the implementation. Problem statement. We does have a study on the impact of the support size fixed on the CSRBF functions on the BEMD. Then I will present our contributions, which concerns the BEMD CSRBF with a support size based on the distribution of the extrema. Then I will see results and discussion. Finally, I end with a conclusion and some perspectives. So, when the signals are non-stationary and non-linear, and we have a priori no idea about their characteristics, the technique time frequencies analysis such as Fourier transform or wavelet remain unsuitable for this kind of signal despite their development. Therefore, a new technique of time frequencies analysis has been invented, called Bidimensional Empirical Multimodal Decomposition (BEMD). It is a method of image analysis was proposed by Nunes in 2003. This method able to extract different structures of scales and frequencies from non-stationary and non-linear signal modeled in amplitude and frequency. Its bases are generated in an adaptive way that are called intrinsic modal function (IMF). We have an example of the BEMD of the cameraman image. So this decomposition allows us to decompose image into several images from the high frequencies to low frequencies that are called the intrinsic modal functions plus a residue. On the other hand, we can reconstruct our cameraman image by the sum of all EMF and the residue, which is done without loss of information or distortion. We will see in this BEMD algorithm the process to follow to extract the IMF from our image E. Initially, to extract the first IMF, we define the local extrema of the image E, the local maxima and the minima. Then, we construct the upper and the lower envelopes from the interpolation of the maxima and the minima, respectively. And then we calculate the average envelope of 2 envelopes, upper and lower. The candidate IMF is defined by subtraction the average envelope on the original signal of each iteration. By a well-defined characteristics, the real IMF is extracted from the candidate 1. Then we repeat this process until generates all the IMF. This procedure is called shifting process. It should be noted here the shifting process involved the development of the following technique: the technique of to be used to extract the local extrema, the technique to be used to construct the upper and the lower envelopes. However, a real obstacle to the implementation of this method is the execution time, since the major part is done by constructing the envelope upper and the lower. In this context, there are several works to build envelopes, such as the BEMD with the Delaunay triangulation in 2005. A year later, we have the BEMD with finite elements. Then, in 2008, we have the BEMD with max and mean statistical filters, followed by a smoothing operation repeated several times. Despite this work, the RBF function or radial basis function remains more efficient in terms of the quality of their IMFs, despite their execution times. In 2014, the use of RBF function with compact support in BEMD show a significant reduction in the computation cost and keep the quality of the decomposition. But the difficulty with using CSRBF function is the size of the support, and the following will look at the influence of the support size on the BEMD decomposition, especially since the extrema to the P interpolation are reduced during the BEMD. We used the Wendland function phi31, which used in the reference 5. as the CSRBF function. After having underlined the importance of the interpolation phase for the BEMD, I will briefly discuss here the procedure to approach a function f known an scattered point by the compactly supported radial basis function CSRBF function. So it is necessary to choose a CSRBF function which defined in the form of equation 1 in general, and to formulate the interpolation or interpolant in the form of equation 2. So it is clear that we are going to look for the vector alpha solution of the system tree. It should be noted that the CSRBF interpolation matrix is symmetrical, sparse, and the percentage of zeros in this matrix depend on the size of the support size used, which offer more advantage in computation complexity and solving matrix system. So, to see the impact of using the fixed support size of CSRBF function and BEMD, we used the cameraman image of size 128 with wavelength function phi31 used in reference 5 as the CSRBF function. Table 2 show that the development of the number of extrema, either the maxima or minima, remains stable, especially from the third IMF between 136 and 156 for maxima and between 119 and 121 for minima, with an execution time of 10.3 seconds. Size of support 20 table 3, we found that the development of the number of extrema is faster, but in the last two IMFs it remains stable with fewer extrema, with an increase in execution time at 19.34 seconds, which is logical when we use a large support size of the CSRBF function and interpolation phase. Here we have the BEMD decomposition corresponding to this result. We note that in the both cases, whether the support size is 10 or 20, the decomposition find the difficulty of extracting the frequencies from second IMF. This result shows that the BEMD CSRBF with the size of the support is fixed. We have the number of extrema remains stable from the second IMF. Difficulties of extraction the low frequencies. In this context, we will use an adaptive and dynamic support size to address the problem of extraction low frequencies. This support size is adjusted according to the number and distribution of extrema to be interpolated, such as used in reference 4. Indeed, after extracting the maxima from the original image, and for each maxima element, we calculate its Euclidean distance to the nearest element. We then obtain a table of distance called the table of adjacent maximum distance. In the same way, we will calculate the table of adjacent minima distance. So, the support size can be calculated in the following 4 ways: D1 to D4. So, to extract the first IMF, we used one of the distance presented in FA BMD, which is based on the distribution of extrema. Knowing that the extrema decrease progressively during the decomposition, we simply multiply the initial support size by 2 after extraction each IMF. Then, from the second IMF, the size of the support is estimated without recalculating the previous distance or using data partition approach that avoid increasing the complexity of the calculation. So, our method then follows the following steps: identify the extrema about maxima and minima of our image I using the neighborhood windows approach to extract the 2D extrema points. Determine the initial support size theta using one of the distance from reference 4. Generate the force IMF with a CSRBF function using the initial support size data. Generate the K IMF with a support size equal to the power K minus 1 multiple data. So here are the results of decomposition of the same previous image cameraman with an initial support size based on the distance 4, which is the largest. According to table 4, we observe that the number of extrema during BEMD is gradually decreased from the force IMF 708 for maxima and 694 for minima to the force IMF 9 for maxima and 10 for minima. This type of evaluation allows us to extract the low frequencies, as we say in figure 5. We also noted that the calculation time is 12.19 seconds. It's acceptable, especially since we have ensured the extraction of low frequencies. In addition to truly evaluate our approach, we conducted a comparative analysis between the IMFs generated by the new BEMD method and those produced by alternative methods such as fast and adaptive bidimensional empirical mode decomposition using order statistics filters introduced by Boyan in 2007 called FABMD, and a fast bidimensional empirical mode decomposition based on variable neighborhood windows method introduced by Ma in 2019. The selection of these methods was based on their effectiveness and rapidity compared to other BEMD approaches. On the other hand, we chose the synthetic texture image STI because it enables us to evaluate the STA with 56 to 156 pixels is displayed in figure 6. The equal size components are added to produce it. Figure 6E illustrates the higher frequencies CI1. Figure 6B illustrates the middle frequencies as CA2, and the figure 6C illustrates the low frequencies SI3. Table 5 presents the global mean of each component SCI and orthogonality index values of the STI image. The synthetic texture image in figure 6D was used to apply a new algorithm. Figure 7 shows the decomposition of this image by the FABMD method, and the decomposition corresponding the BMD VNW are represented in figure 8. Finally, figure 9 presents the decomposition using the proposed BMD. We observe that all three methods generated 3 IMFs, which is the same number as the original STI synthetic texture image. This indicates that the method is also switchable, and figures 7 to 9 demonstrate that the IMFs resembled the original SCIs. To conduct a more thorough evaluation of the novel BMD and the two other BMD methods, Table 6 presents the number of accurate IMFs, the time required, and the orthogonality index values of the decomposition of the STI for each algorithm. We observe that the number of IMFs remains 3 in the proposed BMD and other method of BMD. Compared to the execution time and orthogonality index value, we observe that the suggested approach has an improved execution time of 3.23 seconds and a more effectively orthogonality index value of 0.5. In general, these characteristics indicate that the proposed method is an appropriate choice for the decomposition of the synthetic texture image, in comparison with the FA, BMD, and the BMD BNW algorithms, knowing that the orthogonality value and the time required for the corresponding novel method are less than those corresponding to other BMD. In conclusion, we can say this method with dynamic support size allows us to decrease the number of extrema progressively, which always us to extract all bounded frequencies of image. Without perspective, we can defend and pave the way for future studies to explore further optimization, real-world application, and robustness testing, ensure that the BEMD CSRBF with the dynamic support size method can be effectively utilized across diverse fields. Finally, here are the references used in this presentation, and thank you for all.